So in the previous video, we integrated a function of two variables with respect to x. Now we're going to do the same thing, but with respect to the variable y. And so playing kind of the same game we did in the previous video, just to emphasize certain aspects that I think are important. Let's go ahead and take the partial derivative of this function with respect to y. So when we take the derivative with respect to y, we hold the x as constant coefficient on any y terms that we have. So x here is being held constant. We get 2xy. And because x is a constant, the derivative of x squared will just be 0. So we lose this function. And in fact, we could put any function of x there that we want. Square root of x, fourth root of x, sine of x. Any function of just x would have a derivative of 0 with respect to y. So if we then integrate with respect to y, so we have dy here instead of dx. If we integrate our partial derivative, we'll be integrating the derivative 2xy with respect to y, so dy. And we know that we can factor constants out in front of integrals, so we're holding x as a constant with respect to y. So a 2x can factor off that integral. We're left with y dy. And then when we integrate the function y, oh boy, I hate it when it does that to me. Y dy equals, when we integrate with respect to y, we'll still have our constant out front times the antiderivative of y, which will just be 1/2 y squared. Notice that we don't get the x squared back. We're integrating with respect to y. There's no way without seeing the x squared to know what our function started with in terms of just functions of x. Any function of x would have evaluated to 0. So we wind up having to put that constant of integration on. And what we want to recognize is that constant of integration is really some function of x, which we, without seeing it, have no way of knowing what it was. And then we can simplify this a little bit. 2x times 1/2 y squared is x y squared. So the part that was a function of y, we get that back. The part that was just a function of x, we don't have any way of getting that back. If instead we evaluate a definite integral, so we take our partial derivative with respect to y, but we integrate it from y equals 0 to y equal x squared. As in the previous video, what we want to recognize is that when we're integrating with respect to y, no y's can show up in the limits of integration, only constants or functions of the other variable x in this case. So the other independent variable can show up in the limits of integration, but y cannot show up in the limits of integration. So partial derivative with respect to y, so we're going to be integrating the function that we get here, the xy squared dy. We won't have the constant because we're doing a definite integral. So pull this down here. So when we, oh my word, we're integrating this thing, 2xy dy, but the result of the integration, this is what we're integrating, but the result of the integration is not going to be any different than it just was, except we don't get the constant of integration because we have a definite integral. We're running that integral from 0 to x squared, and this is really running from y equals 0 to y equal x squared. So because we integrated with respect to y, everywhere we see a y, we replace those y's with the limits of integration. So plugging in the upper limit of integration in for y, we get x times, it's going to be x squared squared minus x y squared, but the lower limit of integration is 0 squared. So we're going to wind up with x squared squared, which is x to the 4th, times x is just an x to the 5th power.